Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashidu Mamburu. This lesson is brought to you by the Gauteng Department of Education in collaboration with the Cybono Discovery Center. Today, learners, hoping you are excited. You have a pen, you have your notebook, you'll be taking some notes, you'll be underlining relevant issues so that at the end of this day, you know reactions of organic molecules. So remember, when you were defining the functional group, you said the functional group is a bond, is an atom, it's a group of atoms that determines the physical. When you say physical, we are referring to physical properties, which what you did in question 3. Now, today we'll be focusing on chemical properties, which in this case are reactions of organic molecules, meaning that when we're dealing with these reactions, we'll be focusing on those functional groups. We'll be focusing on those bonds, the atoms, the group of atoms that will tell us what type of reaction and a compound will undergo. So it's very much important to know that as we are doing reactions now, here we have breaking of bonds. Remember, when you're doing physical properties, we're saying we don't break the bonds, but we overcome the intermolecular forces. The language changes here. We break bonds and we form new bonds. So all bonds are broken down and new bonds are formed. But we are focusing on the functional group, which is your bond, your atom, your group of atoms. That will determine the chemical properties. I hope this lesson will help you. And after this lesson, you'll be ready to answer as many questions as possible. It's still part of paper 2, and this is the structure. As always, we always remind you that you will always have multiple choice questions. You will have structured questions, which is 130. The total is 150 for 3 hours, and that is the structure of the paper that you're expecting. The question that we're focusing on, reactions of organic molecules, is question 4. So you can see that of the 3 organic molecules topics, which is question 2, question 3, and question 4. Question 4 is the least where learners are performing at 49% last year in 2024. But I know with you, it will even be much better. After this lesson, you'll even be more confident and be able to do well in terms of the reactions. It's not a difficult topic, but it needs you to have the understanding. So the things that you must be able to focus on this topic will be the reaction condition. Because remember, for a reaction to take place, there must be a condition that is necessary for that particular reaction to take place. You will see, we'll be talking about the reaction conditions for all the reactions that we are going to do. So it's important that you know which reaction condition is good for which reaction. So I'm emphasizing that if you know the reaction condition, you will know the type of reaction. And we'll be focusing as well to say, since we are doing the 9 homologous series, which is your AAA, your alkanes, alkenes, and alkynes, your haloalkanes, your aldehyde, your ketones, your esters, and your alcohols and carboxylic acid. It's good that you must know what type of reactions will the alkanes undergo. So the alkanes, we're going to look at them and the type of reactions that the alkanes will undergo. We're going to look at the alkenes, the type of reactions which they will undergo. The alkenes, you'll see they are very good. They will undergo addition reactions. So we'll look at all the reactions which alkenes will undergo, the reactions which alkenes will undergo. And then we won't focus on the reactions of alkynes. We'll focus on the alkenes and the alkanes. As well, we'll go and look at the reactions that the haloalkanes will undergo. You will see haloalkanes are going to undergo reactions like substitution and elimination. So we're going to focus on that. And then we're going to look at esters and how esters are formed. I think we've done that. Esterification is the process where we form the ester. So you know esters are formed during esterification, which you said is when an alcohol is reacting with a carboxylic acid. We said we use a primary alcohol and a carboxylic acid. They are able to form an ester and water. And the process, we call it esterification. Now we're going to look at the reactions of alcohols elsewhere. You will see that your alcohols will be able to undergo elimination, will be able to undergo substitution as well. So there are those two reactions that you know that alcohol will undergo those reactions. Carboxylic acids, they are involved in the formation of esters. So we're saying when you have a primary alcohol, you add it with the carboxylic acid, we're going to deal with ester. So we only use primary alcohols for the esterification for grade 12. However, as we move on, you might find even much difficult questions when you go to university. Now we are saying this is the topic now, reactions of organic molecules, which is now question 4 for your paper 2 question paper. So we're expecting that you will do very well in this topic, and then we're going to take you through, listen and have understanding. You know, we want you to have conceptual understanding. We don't want you to cram. We want you to know what is happening, so that even when you get a different type of a question, you are able to respond to that particular question. So it's very much important that you don't cram, you have understanding. When you say what type of reaction is this, you must be able to have understanding to say, what do I look at? For example, here we're saying classifying reactions. How will you know whether the reaction is elimination, substitution, or addition? How will I know? So that is the question I'm going to respond to with these 3 slides that are coming, to say, how will you know that this is elimination, this is substitution, this is addition? Let's look at this one. We have put 1 in. Remember, put 1 in. If you can write its molecular formula, it's very much important. Hence, when we started with this lesson, we said that you must know the molecular formula, structural formula, you must know the condensed structural formula, you must know the empirical formula, as well as the general formulas of all these 9 homologous series. So when you're given a structural formula like that, you can write down the molecular formula, because molecular formula, you're saying what type of atoms do we have, and the number, how many hydrogens do we have, how many carbons do we have. That is molecular formula. So our molecular formula here would be C. How many carbons? Is 1, 2, 3, 4. So you know that this is a C4. How many hydrogens? You count them. 1, 2, 3, 4, 5, 6, 7, 8. Then you know that this is a C4H8. So that is the molecular formula of put 1 in. It's 1 in because the double bond is in carbon number 2. Remember, if we move the double bond to carbon number, double bond is in carbon number 1, we call it put 1 in. But we can move the double bond to carbon number 2, then it will be called put 2 in. That's why we're saying put 1 in and put 2 in are positional isomers. So those are things that you must always remind yourself about. Now, we have a C4H8, which is our molecular formula. Sorry, let's move now to our product, which is 2-chlorobutane. Now, how many carbons? If you check, we're still having 1, 2, 3, 4 carbons. So it's still a C4. And then how many hydrogens? Now we're having 1, 2, 3, 4, 5, 6, 7, 8, 9, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 hydrogens. And we have a visitor now called chlorine, because we didn't have chlorine that side. So now if we check the difference between C4H8 and C4H9, you will see that we have added 1 H, hence we have H9 there, which means there was H that was not there, and there was Cl that was not there. So you're able to see that we added HCl. So this must be an addition reaction. You see, just by writing the molecular formula, you are able to classify, because you are looking at structural change, to say what changed in the structure. What changed is that we had 4 carbons, we had 8 hydrogens. What changed now? We have 1 hydrogen extra and a chlorine, which we said is a substituent. So it's very much important to have that, to say, okay, in carbon number 2, we have added a chlorine there. Hence now we are saying this is 2-chlorobutane. So we are saying this is addition. You see, before you even ask somebody, you are able to see by looking at the difference in the molecular formulas of these two, you are able to see or to classify the type of reaction that took place. We're going to talk about how those reactions take place, but now we are still saying, how will you know what type of reaction? So you will look at the molecular formula of put 1 in, molecular formula of 2-chlorobutane, and you check what is different between them. And we're saying the difference is HCl. So you know that HCl was added. I think we are together in terms of that one. Let's move to the next classification. How will you classify this one now? You will do the same. We're still given the same C4H9Cl. You can see we still have 2-chlorobutane. But now what do we have this side? we're having now C4H8. So what is the difference? You can see that there was HCl here, but HCl here was removed. HCl was removed. So you can see that, oh, this must be the removal or the elimination of HCl. So we'll call it dehydrohalogenation when you start doing the reactions. But now, for now, I just want you to be able to see that, okay, we had HCl that has been eliminated. And you see that when we eliminate, we form a double bond. When we eliminate, we form a double bond. But you saw that when we add on the double bond, and then we're able now to have a saturated compound. So I think now you can see, and you are able to see that you can classify the type of reaction by looking at the molecular formulas of the two. The difference there will tell you whether it was addition, whether it was elimination. Now let's look at the last part of our classification of reactions. Now look at this one. It's still our 2-chlorobutane, which we said is C4H8. We said is C4H9Cl. C4H9Cl. And then this side now we have 1, 2, 3, 4 is C4 1, 2, 3, 4, 5, 6, 7, 8, 9 C4H9OH, which now is an alcohol. But you can see that we replaced chlorine there by OH. So you are able to see that this must be replacement. Do we have a reaction called replacement? We call it substitution. So the correct name would be, this is substitution. What did we substitute? We substituted chlorine by OH, or by the hydroxide ion there. So you are able to see the type of reaction. You are able to classify the reaction by looking at their molecular formulas. I hope that will help you, and you will never get reactions wrong. You will be able to see that, okay, we had a chlorine and we replaced that chlorine with the OH, and you are classifying it as replacement, which is substitution. So we are going to be discussing each of these three types of reactions individually to say, look at this reaction, how will you go about that? From there, we'll be able to answer questions, different questions, and give you strategies to say, how do you answer these questions? I hope you are excited and you can see how simple it is to determine or to classify the type of reaction that has taken place. Now, we start with addition. You know, addition is the simplest thing. When you are adding two things, when you are having two substances, you are adding them together, you end up with one. When they are added together, they become one. You can see as we add, that's what happens. The examples that we have given here, we're saying, when you talk about addition, we're talking about alkenes. It is alkenes that undergoes addition. We add on the double bonds for grade 12. We add, but you'll see as you go to university and continue with your studies that we add even on the alkynes. But for your syllabus, we are focusing on addition on the double bonds, which are on alkene. So when you say an alkene, you know it will undergo addition. No alkene, no addition in terms of our syllabus. We add for question 4, we are adding on the double bond. I want to emphasize that to say when you see a double bond, you know that the reaction that that alkene will undergo, it will be addition reaction. Hence, we try to simplify you to say USA there, to say when you have unsaturated becoming saturated. When you're having a double bond becoming a single bond, we call that addition reaction. So addition reaction, you can see we're having here, we're having our alkene here, which is ethene with 2 carbons, and we are adding Cl2. And when we add everything. So when we add Cl2, it's easy because Cl2, one Cl to this carbon, another Cl to another carbon. So you're just sharing them. Then you are able to have now your dichloroethane. So you have your dichloroethane that is formed there. Now, always we are adding on the alkene. We're using ethene as an example here. And then we're saying when you add hydrogen there, one hydrogen on the one carbon, the other hydrogen on another carbon. It's always easy when you are adding a diatomic molecule because they are the same. So on the double bond, you add the other one on the other carbon, the other one on the other carbon, the ones that have the double bond. So it's easy when it's Cl2, when it's H2, it becomes easier because you know that now you add one on the 2 carbons that are closest to the that are having the double bond. Now, when we add halogen, we call the reaction halogenation. When we add hydrogen, we call the reaction hydrogenation. Now, intentionally, we have put now this reaction as number one, the halogenation. Why I said you put halogenation as reaction number one? We're putting halogenation as reaction number one so that you don't forget. This is a spontaneous process, which means that here we need not add, we don't need a catalyst for the reaction to take place. It will take place. So when we are checking for the saturation or unsaturation, we are able to add bromine water there where to check whether we are having an alkene. And always when we add the bromine water, you will see that the alkene now, the color will change. It will become colorless. Now you know that there was an alkene there, and then we are able to check that we have a double bond, that is the addition reaction is taking place. So it's important for you to have that understanding to say we will always add on the double bond, and the type of reaction depends on what we are adding. So we had Cl2, hence we call it Cl2 is a halogen, and then hence we call the reaction halogenation, and no reaction condition. So the first reaction, we're saying there is no reaction condition, the first addition reaction. Now, when you look at the second addition reaction, we are adding hydrogens from the atmosphere. Remember H2, we are saying this hydrogen, and then because we're adding hydrogen, we call it hydrogenation. And then this second reaction of hydrogenation, it does need a catalyst. So the catalyst is either you will use platinum, palladium, or nickel. You need not write the three of them. When we ask you what is the catalyst, you will write one of them, the one you like most. Like me, I like nickel. I don't know for what reason. I will say, what is the catalyst? I will say it's nickel for that one, because it's one of those three. So the first one, we said no reaction condition that you have to mention. The second one, which is hydrogenation, we said you can use platinum, palladium, or nickel. Now let's go to the third reaction. On the third reaction, which is hydrohalogenation, we are taking one from hydrogen, one from chlorine. So it's just a combination. Now we're having ACl. But now, because all of these carbon, they are all carbon number one. They can be carbon number one depending on your choice. So we're saying when you add ACl, it's easy. On one carbon, you will add the hydrogen, which is CH2, becomes CH3. You can see that there is an H there that was added. On the other carbon, you will add Cl2. So you become CH3, CH2, Cl. Hence, we call it hydrohalogenation. And we are saying the reaction condition for this one, no water must be present. So if there is water, you will know the water will want to add itself on the double bond. So we're saying no water must be present so that we can have hydrohalogenation. Now, the last reaction under additions, we are looking there at addition of water. I would like you to have an understanding that when we say water, we are referring to H and an OH. So look at water in that way, that we have H and OH. So we're adding H and OH, meaning that on one carbon, we'll add an H, on the other carbon, we'll add OH. Then you are able to get CH3 and CH2OH. So we have added the water there. So when we add water, we call that hydration. And we are saying the catalyst that is needed is sulfuric acid. Now, to remind you, we said the first reaction that we have done is called halogenation, which I can just say hello. So when I say hello to you, you will say hi 3 times. What are the hi standing for? They are standing for the hydrogenation, hydrohalogenation, and hydration. So you know that we have 4 addition reactions, which is halo and 3 highs, which is now halogenation and 3 hydrogenation, hydrohalogenation, and hydration. So it's 1 halo and 3 highs. So always remember that we have 4 addition reactions that we do under organic molecules for grade 12. And you got to know them. We are saying the first one, the halo, no reaction condition. All the highs, they have reaction condition. And we are saying for hydrogenation, you can say platinum, palladium, or nickel. For hydrohalogenation, we are saying no water must be present. And then the other, for hydration, we are saying sulfuric acid is a catalyst. Now, learners do make a mistake of thinking that reaction condition is a catalyst. So I want to emphasize that. Remember that a reaction condition is the condition that will allow the reaction to take place. So a catalyst becomes a reaction condition, but a catalyst is not a reaction condition. So I want you to have that understanding so that you are not confusing the two. To think that if we say now sulfuric acid is a catalyst, and if we say no water must be present, we're not saying no water must be present is a catalyst for that reaction. It's a reaction condition. It's the condition that will allow that reaction to take place. Is that we must prevent water to be present in excess there. If we have a lot of water, the water will add in the double bond. So the condition for hydrohalogenation is that no water must be present. But the catalyst for hydration, it is sulfuric acid. I hope you got that and you will move with it. So always remember that we are saying that the first reaction, the first halo, no reaction condition. But for hydrogenation, we are saying there is nickel, there is platinum, there is palladium. Now for hydrohalogenation, we said no water must be present. And for hydration, remember, hydration is when you are adding water. When you add water, we're saying that sulfuric acid must be there as a catalyst. So if you want to remember, you will say, okay, the first one, no reaction condition. And then this one, you say nickel. What is nickel saying? No water must be present where? In SA, which means that sulfuric acid is our catalyst. So always remember that we have no reaction condition for halogenation. We have nickel as a reaction condition for hydrogenation. We have no water must be present for hydrohalogenation. We have for hydration is sulfuric acid. Now I want you to have an observation to say almost when we have water involved, you will see that sulfuric acid will be around, with the exception of substitution reaction. You will see when you deal with substitution, even though we are having water, when you are doing hydrolysis, you will see that we don't have sulfuric acid as a catalyst, but we will talk about that when we reach there. But you will see that during your elimination, during your addition, if water is involved, you'll see that sulfuric acid is around. You have seen it even during esterification. We said the catalyst is sulfuric acid. So you must know that when I see water, I can see sulfuric acid around, because you know it's a nice dehydrating agent. So it's very much important to have that in mind, but know the limitation to say sulfuric acid cannot be a catalyst during substitution. We'll talk about it, but you know that during addition and during elimination, sulfuric acid, when there is water, becomes our catalyst. And during esterification as well, water is being produced there, we're saying sulfuric acid is our catalyst. So I've given you 3 reactions where we use sulfuric acid as a reaction condition or as a catalyst. So you will always remember that sulfuric acid is very much important, because it allows some of these reactions to take place. Esterification, we are saying we need sulfuric acid as a catalyst. Addition of water, we need sulfuric acid as a catalyst. You will see when we do elimination of water, you will need sulfuric acid as a catalyst. So sulfuric acid for those 3 reactions, always have that in mind, because if you know the reaction condition, you will know the type of reaction that will take place. I hope you have understood this type of reaction, which we call addition type of reaction. And the last thing I want to talk about now, when I conclude on the addition reactions, and then we're going to do questions now, so that you learn how to answer exam type questions and how this addition occurs. Now, if we check the first one, we said is halogenation. Halogenation, we are saying is addition of X2, addition of a halogen to alkenes. So if we say define halogenation in terms of the addition reactions, you know that it's addition of X2 to alkenes. Why am I'm being specific here to say in relation to addition reaction? When you add X2 or when you add a halogen to alkenes, you are doing halogenation. Hydrohalogenation is addition of H2 to alkenes. Hydrohalogenation is addition of HX or HX to an alkene. Hydration is addition of water to alkene. So know this type of reaction, because sometimes will ask you to define this type or describe them, this type of reactions. So it's good that you always have that understanding of what is halogenation, what is hydrohalogenation, what is hydrohalogenation, what is hydration. So you're always able to differentiate them. And as I conclude, I'm saying always remember the reaction condition. To say the reaction condition for halogenation, which we said we use it for when we use bromine water to check for that saturation, we are saying that it's important for you to know that here we don't have a reaction condition that we expected to know. But in terms of hydrogenation, we said nickel, platinum, palladium, or nickel. And for hydrohalogenation, we said no water must be present, and for hydration, sulfuric acid must be present. Why am I emphasizing this? Remember, when we give you questions, you are going to see. Sometimes we'll just give you a compound, we just call it compound A, for example, and then we give you the reaction condition. The reaction condition will tell you what type of reaction is that compound undergoing. So it's very much important that you understand the reaction condition. Now, as I indicated, that we do four addition reactions, which is halogenation, hydrogenation, hydrohalogenation, and hydration. Now, I want to bring this to your attention to say, if you look at this structure, it's a structure of but 2 in, which means the double bond is in the middle there. And this structure, we say this structure is symmetrical. I found that this is very much important to understand the issue of symmetry. To say when the structure is symmetrical, what does that mean? When the structure have the same substituents at each end of the double bond. If you look at the double bond here, you have CH3 on the left there. You have CH3. You look on the right of that structure, you have CH3. So you are able to see that this is a symmetrical alkenes, which means on the either side of the double bond, you find that you have the same substituent. Now, what does that mean? It means when you are adding on such a structure, it's not a problem, because you know that when you add H2, you'll just add one H on the first carbon and another H on the second carbon. The same when you are adding Br2, you'll add Br on the first carbon and the other Br on the third carbon, on the second and the third carbon. When you are adding HBr, it doesn't matter. You just have to add them on the double bond. So you are not worried here to say, where will I put the H? As long as you put them on the double bond, you'll be correct. Hence, it becomes easier for you. You can put BRH, that's on the carbon number 2, Br on carbon number 3, or vice versa. It's not a problem because the structure is symmetrical. Now, if you are adding water, the same. You will add H on the second carbon and OH on the third carbon. It's not a problem, or vice versa. But now, we will see now when we are going to deal with structures that are unsymmetrical. That's where the chemistry is. That's where the chemistry is, because now we're going to talk chemistry here. To say, I want to add Br and Br on this double bond, on these two carbons that are having a double bond. I can only add on these two carbons that are having a double bond. So because Br and Br are the same, it doesn't matter. I'll just put one Br on the first one, the other Br on the second one. Remember, when you add, you are breaking the double bond. You won't have a double bond, you now have single bonds. Hence, I'm going to add the Brs on these two carbons that are having a double bond, because I'm getting rid of the double bond. And when you add everything. Remember, I'm having Br2 here. It means I have two reactants, which is this one, which is our organic. We're having our organic molecule, which is put one in. It's our organic molecule. It's reacting with an inorganic molecule. Remember, it's important to know that this one is inorganic and this one is organic. Remember, we said organic molecules, they contain carbon, and molecules containing carbon. It's very much important. So this one doesn't contain carbon, so we refer to it as an inorganic molecule. So we're adding an inorganic molecule, but this is Br and Br, it is the same. So it's important to say we'll add, I'm going to write carbon number 1. But because when we add, we are breaking the double bond. I can't write the double bond, I'll write a single bond. And then we're going to add one Br on this carbon. The one with the double bond, the first one, which is this one. And then I'll add another Br on the other carbon. And then we're able now to get our structure, which is 1,2 dibromobutane. So you can see that now we were able to add, because we were adding same thing, we're adding Br and Br. It doesn't matter, you just put, as long as you add on the double bond, you put the two Brs there, you have added, and you got your product. And then you can see we're having an alkene, which was put one in, and then we have changed now the suffix there. It's no longer an alkene now. Now it's 1,2, 1,2, let me write it here, 1,2 dibromobutane. So you can see that we've changed a butene to a butane because it has undergone a reaction. After that reaction, we've changed the suffix, we've changed the homologous series. We no longer have an alkene, we have a haloalkane. So you can see how these reactions occurs because we are mostly changing the suffix there. Now, if you have to add the hydrogens, it's the same. You will just add one hydrogen on the first carbon, one hydrogen on the second carbon. Then you are able to get the two carbons and then the four of them. Then you are able to put them 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, like that. And then you have added your two hydrogens on the double bond. So because they are the same, no problem. You just have to add one on the other carbon, one on another carbon. I think you have understood that, and it will help. And did we change the surname or the suffix? Yes, it was but1 in, now is butane. So you can see that, oh, these addition reactions, we are changing the suffix, we are changing the homologous series, we are changing the functional group. Remember the definition of functional group? We said it's a bond, it's an atom, it's a group of atoms that determines the physical and chemical properties of an organic molecules. So how this double bond behaves is because of the bond. Hence, we're saying a functional group is a bond. That double bond, it is our carbon-carbon double bond, it is our functional group for alkenes. And during the reactions, it is that functional group that will undergo reaction and it will change from its original functional group to a new one. Because we are adding on the functional group, now it becomes an alkene, as you can see there. I hope you got it. Now, the chemistry is on these two. When we are adding a hydrogen and a halogen, what we call hydrohalogenation. When we are undergoing hydrohalogenation, you will see now that we have two options. We can put the H on the first carbon. You can put the Br on the second carbon. Or we can put the Br on the first carbon and or put the H on the second carbon. You see, now we have to know, where do I put the H, where do I put the Br, and what informs where the hydrogen will go and where the bromine will go. Now, what happens here, we are using what is called Markovnikov's rule. So Markovnikov's rule is saying, when you are adding, hydrogen will go where there are many hydrogens. Hydrogens will go to the carbon that has many hydrogens on the double bond. Remember, you can't add if you don't have a multiple bond. There must be that multiple bond. The multiple bond is in carbon number 1, between carbon number 1 and carbon number 2. So, hence was going to say, when you are adding HBr, you want to add it on carbon number 1 and carbon number 2. But we are saying, according to Markovnikov, for us to get a measure product, that's why here I wrote measure product, because I want us to talk some chemistry there. To say, for the measure product, we must hydrogen must go where there are many hydrogens, which means I'm going to now have 3 hydrogens on the first carbon. I'm going to have 3 because according to Markovnikov, the hydrogen will go where there are many hydrogens. So you can see there were 2 hydrogens came there. So we're saying the rich becomes richer. So what happens? We're having now carbon number 2. What will go to carbon number 2 is the Br. Remember, we're adding HBr. H to the first carbon. Hydrogen goes where there are many hydrogens, and the Br will go where there are less number of hydrogens, which is carbon number 2. And then you're able to write the rest of the structure. I hope you are understanding and you are enjoying your lesson. You are writing some notes so that you don't forget what I'm saying, so that when you are doing these reactions, you are able to know. When we have an unsymmetrical alkene, which means now when we have the substituent on the either side of the double bond, when they are not the same, because you can see on the left we have CH2 only, on the right we have CH, CH2, CH3, which means it's unsymmetrical. And when it's unsymmetrical, we use Markovnikov's rule. We won't be asking you Markovnikov's rule in the exam, but you must be able to know the application of it to say the hydrogen will go where there are many hydrogens. I'm overemphasizing that because that is where the chemistry is, and you are able to see that, okay, the hydrogen will go where there are many hydrogens, the bromine will go where there are lesser number of hydrogen. Now, we call that a major product. So I don't want you to be confused. It means there exists a small percentage of products that will be formed that we refer to as a minor product. But when we're asking you a question, we're asking you about the major product, which is this one. But there is a minor product that is formed, and we want you to know about the existence of the minor product. Because if now they ask you a question about the minor product, you can't say, I don't know the minor product. I only know Markovnikov says the hydrogen must go where there are many hydrogens. So the minor product is when the hydrogen will go where there is lesser number of hydrogens, which means now the hydrogen will come to carbon number 2, the bromine will go to carbon number 1. We call that minor product. So I want you to know that we have the major product and the minor product. But for now, I want you to focus on the formation of the major product, because when you understand the major product, it becomes easier for you to understand the minor product. So, okay, the one that does not follow Markovnikov's rule, it means that that will be the minor product, where hydrogen will go where there are lesser number of hydrogen. So you see on these two carbons, we're saying the hydrogen will go where there are many number of hydrogens according to Markovnikov's rule. And then carbon number 2 has a lesser number of hydrogens, hence bromine will go to carbon number 2. So hence we are forming that 2-bromo butane. Now it means if you form 1-bromo butane, it means that will be a minor product. 1-bromo butane will be a minor product because now it didn't follow the Markovnikov. It means that the hydrogen is no longer going where there are many hydrogens. So if the bromo comes to carbon number 1 and the hydrogen to carbon number 2, we call that minor product. But the questions, when we ask you, majority of our questions are based on the major product that follows Markovnikov. So don't forget, we are saying hydrogen will go where they are to the carbon where there are many hydrogens, and then the other one, which is bromine in this case, will go to carbon number 2 because there is only one hydrogen. I hope you have understood. You would always know that hydrogen where there are many hydrogens, even hydrogen will go so that the richer becomes richer. I hope you got that. Now, when we are adding water, is the same. I said when you see water, you see H plus and OH minus. You see hydroxide ion and hydrogen joined together so that you don't have confusion, because now you want to add OH and H. That's what you are adding. OH and H. Where will the hydrogen go? Where will the OH go? I can hear you saying that where you are now. You understand that the hydrogen will go where there are many hydrogens according to Markovnikov, meaning that we are going to have on the first carbon, we'll have 3 hydrogen because hydrogen will go where there are many hydrogens. And then on the second carbon, we're going to have OH because the hydroxide ion will go where there are less number of hydrogen. I think you got that. And then we have our beautiful structure there that we refer now as butan to all. Butan to all. You see how I'm drawing the structural formulas? I'm showing all the bonds, because when you draw the structural formula, you would always show all the bonds, even the bond between the O and the H, so that you don't have confusion. So you can see that butan to all is formed. Don't forget reaction condition. We said the first reaction, no reaction condition. The second one is nickel. Who is saying what? Nickel. Nickel is saying no water in SA. Nickel, no water in SA. So you are able to remember that for hydrogenation, we use platinum, palladium, or nickel, one of those 3. For hydrohalogenation, we are saying no water must be present. And then for hydration, you know, hydration, water, sulfuric acid is around where water is. We said with the exception of our substitution reaction because they don't use they don't use sulfuric acid as a reaction condition. We will talk about it when we do that reaction. I hope you are happy now with addition. You are happy with Markov-Nikov. You know that the unsymmetrical alkenes are the ones where you must check the carbon with many hydrogens, because the carbon with many hydrogens is where we'll add the hydrogens, and the carbon with the lesser hydrogens will add the other, either a halogen or the OH. So always have that in mind. Now, you have seen now, as I conclude this part, to say it is alkenes, it is unsaturated hydrocarbons that becomes saturated, and the reaction is called addition. The second thing you have seen is that we do halogenation and three highs, which is your hydrogenation, hydrohalogenation, and hydration. The last thing, we emphasize the issue of the reaction condition to say for halogenation, no reaction condition. For hydrogenation is platinum, palladium, or nickel. For hydrohalogenation, we said no water must be present. And then for hydration, we said sulfuric acid is the catalyst. So I hope you are singing now. You are singing addition reactions, and you can't wait to write your tests, to write your exams, so that you can understand, you can enjoy. And we said addition reactions, it is the alkenes that undergoes addition. That double bond we want to add where there is a double bond. Now I'm moving to the second type of reaction, which is now elimination. Elimination reaction. We're saying here, here we are starting with a saturated. It means we have no multiple bonds between carbon atoms. It is only the homologous series that doesn't have a double bond between carbon atoms that undergoes elimination. So it means we are eliminating from our saturated becoming unsaturated and elimination. We only use this for you to remember. It's not necessarily the science that we are teaching you. The real science we are teaching you is that we are going to eliminate in grade 12. We are going to eliminate when we see alkanes, haloalkanes, and alcohols, those saturated compounds. Hence I said aha. So it means when you see alkanes, haloalkanes, and alcohols, you know we're going to eliminate. We can eliminate or we can substitute. So it's very much important to know which homologous series undergoes elimination. I've told you already that it's alkenes that are going to undergo addition. Now I'm adding to that. I'm saying alkanes, haloalkanes, and alcohols. Aha. They will undergo this one's elimination. Meaning that when I see an alkane, I know we can remove the hydrogens there. So it will be dehydrogenation. When you see a haloalkane, I know we can remove the hydrogen and the halo, then it will be dehydrohalogenation. When I see an alcohol, we can remove OH and H. Remember, we don't just remove one. As we added, you saw how we're adding two. Even when we'll remove the two of them there. So I hope you have an understanding. And we're saying elimination reactions is saturated compounds like alkanes, haloalkanes, and alcohol. Hence I'm saying aha, so that you don't forget. These alcohols, haloalkanes, and alcohols, we're saying they undergo elimination. And then we can start now with the first type of elimination that we refer to as cracking. Cracking. We had a question last year about cracking. To define cracking, only 28% of learners were able to define cracking. I know this is not your story. With you, all of you, you'll be able to define what is cracking when it's asked. So we're saying cracking is a chemical process in which longer chain hydrocarbons. So we're talking about longer chain hydrocarbons molecules are broken down. So we're having a longer chain hydrocarbons molecules that are broken down to shorter, most useful molecules. So we're breaking very long hydrocarbons into shorter, most useful molecules, like the ones we use for petrol and other stuff, which is important that we have those shorter molecules because we are able to do that. You'll be able to see when we talk about other type of reactions. You'll see how these shorter molecules help us in things like butane and all that. You know, the firelighters and all that, they're using such shorter most useful molecules. So we're going to demonstrate as well in the lesson so that you see why we need cracking. We need cracking because you'll see when we talk about petrol, we're talking about octane and all that, hexane and all that. You know that now that is shorter, most useful molecules, and we get those molecules through a process of cracking, which is the chemical process in which longer hydrocarbons molecules are broken down to shorter, more useful molecules. I hope we are together on that one. That's what we call cracking. So this cracking, we're having what we refer to as thermal cracking. For thermal cracking, we're using high temperature and high pressure. We don't use a catalyst for thermal cracking. We use high temperature and high pressure to crack, to break down longer chain hydrocarbons to shorter, most useful molecules. Now we have another process which is called catalytic cracking. So we have two types of cracking: thermal cracking and catalytic cracking. As the name said, catalytic cracking, we use a catalyst. Hence, the temperature will be low and the pressure will be low. So there are two of those reactions. And we're saying this cracking process, the cracking process, we're saying the product is either will form an alkane and an alkene, or will form an alkene and hydrogen, one or more. You will see as we do questions what we are referring to. So you know cracking, you can form alkane and alkene, or alkene and hydrogen, which is the process that we call dehydrogenation. Remember, we had hydrogenation when we're adding the H2 to the double bond to the butene, as I was showing you in the previous slide. So now we are able to remove it, and then when we remove it, we call it dehydrogenation, and it's part of our cracking process. Now, as we move, we're able now to say, let's look at how we do this cracking. So I've already indicated all this, so I'll go straight to it. See, for example, we're having ethene there. We're having ethene there, and then ethane there, and then we're saying that ethane, we can be able now to crack it, which means we can be able to remove the two hydrogens there, and then it becomes from C2H6, it becomes C2H4. I think you are learning the importance of molecular formulas to say, if I'm able to check the molecular formulas, I will know the difference. I will know what happened. Because if I give you C2H6 and the product is C2H4 and say, what is the structural change? You are able to say, okay, the H4 is from the H6. So it means we have removed from H6, we have removed two hydrogens. Hence we call it dehydrogenation. The D for the removal of what? Of hydrogens. So you get that. That is dehydrogenation. And then when we're cracking, as I indicated, say we can form an alkene and hydrogen. We can form an alkane and alkene. So let's take butane, for example, and crack it. To say, when we are having butane, which is having 4 carbons, we can crack and remove the 2 hydrogens. So we'll call that dehydrogenation. Remember, we said it can be catalytic or thermal. Now, we can as well crack or remove an alkane from there. So if we cut here on the first carbon, then we're going to get CH4 and an alkane and an alkene. We can even break it down in the middle. Then we're able to get an alkane and an alkene, which in this case is ethane and ethene. So cracking, we have all those options. When we have a light structure, we can remove the hydrogens, we can remove 1 carbon, we can remove 2 carbons, depending on the number of the carbons in the longest carbon chain. So I hope you have understood how we are doing cracking. So I felt it's important that we do an activity that is based on that cracking, so that you have the understanding of how this cracking takes place. So we're given butane is produced in industry by the thermal cracking of long chain molecules, as shown in the equation. X represents an organic compound that is produced. So you can see we're having C10H22. In our case, we do up to C8. So it will be C8H18. And then if you are given this longer carbon chain structure that you are having there, you can see that we had 10, but now we have 4 remaining. So what happens here on X? You can see that that must be C6. And we had 22, we're remaining 10. So you're just using a calculator to say 10 minus 4 is C6. 22 minus 10 is 12. So C6H12. So you can see this is an alkene, hexene, and then this is an alkane, butane. So you're able to see that this is cracking. And look at the type of questions we are asking you there. To say write one condition required for thermal cracking. Remember we said high temperature, because it's not catalytic, it is thermal, this one. The molecular formula of X is C6H12. The homologous series to which compound X belongs, remember we said during cracking, we form an alkane and an alkene. So you're able to say, okay, we have an alkane here, definitely this is an alkene. And you can see it's a CnH2n because it's C6H12. So you're able to say this is an alkene, and you are able to get all your marks. I hope you are happy and you are more confident with cracking, and you would understand if they bring another question on cracking, you will do very well. Now, let's look at other elimination reactions. Remember, we said we don't do dehalogenation. We don't do halogenation. We do it during addition, but we don't do dehalogenation in grade 12. We only remove the other 3. It means we have 4 addition reactions, which we said is halogenation, and we are saying there is no elimination of those halogens. So we don't do dehalogenation. However, we do dehydrogenation, as I've shown you during cracking. We do dehydrohalogenation. We can remove HX. We're able to remove, as we're going to show you on this one. To say haloalkanes, we can be able to remove HX and be able to put that. And then we can be able to remove water from an alcohol. So those are the elimination reactions that we have. So there are 3 elimination reactions. Additions, we said there are 4. But the elimination, there are 3, because we don't do elimination of halogens. We don't do dehalogenation. We do dehydrogenation, dehydrohalogenation, and dehydration. Those are the 3 elimination processes that we have. So I hope you will always have that in mind and you will do well. Now, let's look at this one. We're given CH3CH2Cl forming CH2CH2 plus sodium chloride plus water there. What are the reaction conditions? We are saying for dehydrohalogenation is that there must be heat. When we eliminate, we need heat. We need heat because we want to eliminate. We want to get rid of stuff. So there must be heat, and then under that reflux. But the main issue there, let us know that heat must be there. And we are saying there must be sodium hydroxide, which is sodium hydroxide is your concentrated. Remember, for elimination, we're saying we need concentrated, Ce. Concentrated is for elimination. So once we say concentrated sodium hydroxide, you know we are eliminating here. So concentrated sodium hydroxide or concentrated potassium hydroxide, that is a strong base. Concentrated strong base and heat as the 2 conditions that you will require for this type of reaction. Now you can call it a hot ethanolic sodium hydroxide. Remember, when you say hot, it means you are heating, and then you are saying it's sodium hydroxide, and it must be dissolved in ethanol. Hence, we are saying hot ethanolic sodium hydroxide. For those who want to know it like that, but if you don't want to be complicated, simply say it is heat and concentrated sodium hydroxide are the 2 conditions for the hydrohalogenation. I want to explain this one, and I find it very interesting. Remember, Lenas, we want to remove a hydrogen, as we indicated here with red. We want to remove HBr here, the H and the Br. Now, you know, hydrogen bromide is an acid. It's an acid, strong acid like HCl, strong acid HCl. So you want to remove that acid. Obviously, as a science learner, you know, man, I must need a base to remove an acid. I think it makes it much easier for you to remember that we are going to remove HBr, which is an acid. We will need a base that we'll be using for that reaction. Hence, we are using sodium hydroxide, concentrated sodium hydroxide, because you want the acid to react with the base. You can see the base there. Concentrated strong base is coming to react with that strong acid. Now that will form salt and water. Remember, you have done neutralization. You said it's a reaction between an acid and a base to form salt and water. So this is one of the most important reactions that you cannot forget, because it's the elimination reaction that forms 3 products: 1 organic product and 2 inorganic product here, salt and water. So it's important to see that the sodium hydroxide will take the halogen there to form sodium bromide, and the OH will take the hydrogen there to form water. But now you know the issue of which one is a major product, which one is a minor product. Remember, we talked about that during addition. We said we use Markovnikov, where we have more number of hydrogen. The carbon with more number of hydrogens is where we'll add hydrogens. Under this one, under elimination, when we eliminate, we don't use Markovnikov, we use Zaitsev rule. So according to Zaitsev rule, we are removing the hydrogen from the poorest carbon. We are removing the hydrogen from the carbon with lesser number of hydrogens. So we're not going to remove from carbon number 1 to get a major product. We're going to remove from carbon number 3, this one that we circled here. We're going to remove this one to get a major product. I hope you get that. Hence, we're showing it in red there. To say to get a major product, we're saying the poor must become poorer. According to that, we just say this. It's not what we mean. It's a reminder for you to remember that the Zaitsev rule, when we eliminate from the poorest carbon. We remove the hydrogen from the poorest carbon. So we're not going to remove from carbon number 1 this side or carbon number 4 this side. Why? Because they have more hydrogens. We look for the carbon with lesser number of hydrogens, and that's where the removal will occur. So for major product, you know we're going to remove the hydrogen. The bromine, we know we're going to remove this bromine. But which hydrogen? There are 2 of them there. We're saying for major product, we'll remove the one that is lesser. Remember carbon number 1, it has 3 hydrogens. Carbon number 3 has 2. So we're saying we'll remove hydrogen from the one with lesser number of hydrogen. Hence the double bond will be in carbon number 2, and we call this major product. So when you say what is the product that will be formed, you'll give us the major product according to Zaitsev's rule. Then the minor product is when we remove the hydrogen from the richest carbon, from the carbon with many hydrogens. We call that the minor product. It's just a smaller percentage of the product that is formed, but your focus must be on the major product. So don't forget, as I leave this one, I'm saying you know that when you see concentrated, you know that is elimination. And for us to eliminate, we need heat as well. So it must be concentrated in this direction, concentrated sodium hydroxide and heat. Those are the 2 reaction conditions. Then we know that is elimination. And we are saying we can form a major product and a minor product following the Zaitsev rule, to say the carbon with the lesser number of hydrogens is the one where we will remove the hydrogens from. So I hope you got that. We're talking about the carbons that are adjacent to our substituent, to our bromine. So this carbon and this carbon, those are the 2 that we are checking. Which one are we going to remove between this one and this one? Which one are we going to remove the hydrogen to form a double bond? We're saying we'll remove the one that has a lesser number of hydrogens, which means the double bond is there. I'm explaining a lot so that you are able to get it and you are ready for your exams. Now, our last part of elimination is when we eliminate water in alcohol. So elimination of water from an alcohol, we call it dehydration, because water, we said when we add water is hydration, when we remove water is dehydrogenation. And I told you already that when you see water, think sulfuric acid, with the exception of substitution, so that we don't have problems. So you will know that the reaction condition here must be concentrated sulfuric acid, because we said for elimination is concentrated, is for elimination, and heat must be there. So we're saying this one, there must be heating alcohol with an excess of concentrated sulfuric acid or phosphoric acid, because you will read other books, they will talk about phosphoric acid. So it's important for you to know that we can use concentrated sulfuric acid or concentrated phosphoric acid. The rule is that if more than one elimination product, major product, which I talked about that, to say the major product, the hydrogen atom is removed from the carbon atom with the least number of hydrogens. Hence I said we're having here OH here. So we're looking at these two carbons, this one and this one, to say which one are we going to remove the hydrogen from, because the OH already is that one. We want to form a double bond. We are saying now the carbon number 1 here is richer, it has 3 hydrogens, so we don't remove from it. We will remove from the carbon that is having lesser number of hydrogens. So I just included this on the slide so that you are able to see it clearly when we do the dehydration, the removal of water from an alcohol. So we're going to remove this OH, and we agree that the hydrogen that we'll remove must be from this carbon. So we're going to have a CH3, the first one, this one, we're going to have a CH, we're going to have a double bond now, and then we're going to have a C, another CH, and we're going to have a CH3. So we're forming what is called both 2E as the measure product. I think you have seen that most of the time, if you're having 4 carbons, you'll see that the measure product, when we follow these rules, they favor carbon number 2 to be the one that things are happening there in terms of the changes, in terms of the functional groups. Now, if you check the last one, the minor product is where now we're going now to, instead of taking this hydrogen, we'll take from the hydrogen, this hydrogen here, and then we are able to form the double bond in carbon number 1. But now that is a minor product. If it's very less percentage that will be formed with that. But we want you to know that there is major product, there is minor product, because we want you to have understanding of the chemistry as a whole. Now, once you have done that, we know that you are happy with the reactions. You know, when I see water, I know that sulfuric acid will be my reaction condition, concentrated sulfuric acid. And because it's elimination, we said we are heating here, we heat with sulfuric acid. So you can see reaction condition, easy to remember. I'm going now so that we are able to do the reactions. Then we talked about that the elimination, which you said is cracking, can be high temperature, high pressure, or catalyst can be used. And then it's our dehydrogenation. Dehydrogenation, we said we are able to form salt and water, and our alkene there. Good, we did that. Dehydration as well, like that. So it becomes easier like that as you see the reactions, and then you are able to know that Zaitsev's rule tells us how to get the measure product. I only showed you the measure product here because most of the time we're asking questions about the measure product. Hence, we just want you to, at the back of your mind, to know that there's a minor product. Now, before we can now go to the last type of reactions that we are focusing on today, maybe second from last, which is substitution. Substitution reactions, we are saying here, we're only dealing with saturated. So you will never find unsaturated when you're dealing with substitution. It's saturated, forming another saturated, and it's called a substitution. And it is still remember our that we said these are the ones that undergoes elimination. We said it's alkanes, it's haloalkanes, and alcohols. Those three, they undergo elimination and substitution. So when you see alcohols, when you see haloalkanes, when you see alkanes, you know that these ones, they can undergo substitution or elimination. So it's important to know that, okay, it is the three. Our focus in terms of substitution and elimination is on the 3 homologous series. So it makes things even much easier for you. Now on this one, we are saying alkanes. I said alkanes, they undergo substitution. So we have an alkane there, butane in this case, and then you can see we're bringing Br there. It's just a replacement indeed. We're replacing this hydrogen with this bromine. We're replacing that hydrogen with a bromine there. And we're replacing the bromine there with the hydrogen. So hence we are able to form HBr as well. So we have 2 reactants, we have 2 products that are being formed, which is Br2 plus butane, and then they are coming together, they form a haloalkane and a hydrogen bromide in this case. So you are able to know that, okay, this is a replacement, it is substitution. So we remove the hydrogen there, we have put. Maybe the question that you are asking them, are we following the Zaitsev rule? No, not necessarily Zaitsev rule, but it's just that when we have the bromo in carbon number 2, we have the most stable molecule that we are having. Hence, we are saying that on this one now, the bromo will come to carbon number 2. Why not carbon number 1? when it comes to carbon number 1, it will form 1 bromo butane, which is not a very stable product. The most stable product is when you have formed that 2 bromo butane, but not necessarily. We don't talk ZF here. We talk about the most stable product that is formed. So the major product, which is the most stable one, it is 2 bromo butane. So you'll see after in that substitution, we're following the same road with ZF, but it's not ZF, it's just that the 2 bromo butane becomes the most stable product. Now, this haloalkane can undergo 2 types of hydrolysis. I want you to have understanding that this hydrolysis, we don't call this, some learners, they see water there and then they think about hydration. It's not hydration, it's hydrolysis, because it's not the H2O that we are replacing with. We're not going to take the Br out and put the water. We're going to take the Br out and put the OH. Just forgive me there. You must show the bond between the O and the H at all times when you're drawing structural formulas. Now, we are saying we are going to put the OH where there is bromine, not the water. Hence, we can't call it hydration, because hydration is when you are adding water. We're not adding water here. We are replacing the Br with the OH. Hence, we call it hydrolysis. So I think you got it. Hydrolysis. Hydrolysis is like we're cutting the hydro there, the OH there. We're putting the OH and removing the Br. So we're saying this is hydrolysis. I think you have done hydrolysis, or you will do it when you do your acids and bases, and then you will understand the reaction of compound with water in this case. Now, hence, you know that there are 2 types of hydrolysis. We can use water and mild heat. You see, we have heat under this substitution, but it's just mild, unlike elimination when we use concentrated. So these are the 2 reactions that will determine whether you do well on this section or not. Because if you have understanding of the conditions, they will tell you whether the reaction will be elimination or substitution. Remember, it is alkanes, it is haloalkanes, it is alcohol. So we're saying the condition tells you to say, if we say mild heat, already you know it is substitution reaction. But when you say heat, you know that we are dealing with elimination. And then when you say concentrated sodium hydroxide, you know that is elimination. But when it comes to hydrolysis, we'll say dilute sodium hydroxide, dilute strong base, which is sodium hydroxide. So you're able to see the difference there. And then the first reaction, which is halogenation, we call it halogenation. We said the reaction condition there is sunlight. And the second reaction, we are saying 2 types of hydrolysis. Another one, we are using water. We are not adding water. It's not hydration. It's hydrolysis, because we are replacing the halogen with the OH there. And then the next one, we're using dilute sodium hydroxide. In this case, you'll have your sodium hydroxide there, and then the OH will be replacing your Br from that structure, and then you are able to get an alcohol. Then the last reaction is when we use HBr, when we replace the Br, the OH with the Br, but using HBr. Hence, we don't call it hydrohalogenation. We call it halogenation because we are only replacing the OH with the Br. So hence, we are focusing on what we are replacing with. The OH, you can see here, the OH has been replaced with the Br. You are able to see that we had an OH there. Remember, always show the bond between O and H. And then we are saying here, the Br is replacing the OH. Hence, we call it halogenation. We don't call it hydrohalogenation, because the H is not doing anything. It is the Br that is now replacing the OH, and then hence we are calling it halogenation. So we have 4 types of halogenation, which is now 4 types of substitution reactions, which is halogenation, where we use Br2 or Cl2, and then we are having hydrolysis, and we're saying there are 2 hydrolysis. We said the other hydrolysis we can use water and mild heat, and the other hydrolysis we can use dilute sodium hydroxide and mild heat. So you know that we have those 2, and they all form what? Alcohols. The hydrolysis, they are forming alcohols. So those are the condition, can be water and mild heat, or sodium hydroxide and mild heat. And lastly, we are saying you can bring the HBr to the alcohol, and then you are replacing the OH with the Br, hence we are calling it halogenation. And it is the tertiary haloalkanes that they enjoy undergoing these types of halogenation. The tertiary haloalkanes, you don't even need, when you're having tertiary haloalkanes, not even any other reaction condition is necessary. So I hope this helps you now to understand the three types of reactions, major types of reactions that we dealt with, which is addition. We said it's the alkenes that undergoes addition. We went to elimination. We said, okay, this one is it's alkanes, haloalkanes, and alcohols that undergoes elimination. And the substitution as well, we said it's the alcohols, the haloalkanes, and the alkanes that undergoes substitution. And we are saying during these reactions, what differentiate them is the reaction condition. If we say concentrated, already you know we're dealing with elimination, concentrated and heat. But immediately we say mild, you know that no, we are dilute, you know that we're dealing with substitution. So hence we say CEDS for you to remember. To say concentrated is for elimination, dilute is for substitution. So we always remind you this so that you don't forget. I hope you have enjoyed all these sections. We're going to deal with questions as soon as possible so that we are able now to cover as much as we can. State the use of alkanes as fuels. Write down the equation for the combustion. This is now oxidation of alkanes. So oxidation reactions is when we are having our alkanes plus excess oxygen. So we do excess oxygen in grade 12, and then you are able to form carbon dioxide and water plus energy. For example, propane gas is used in the Bunsen burners. You see the ones you have in your lab, your school laboratories, then propanes can burn as follows. This is the combustion of propane. Now, I want you to understand that propane, you know, is C3H8, as I wrote it there, plus oxygen. It forms carbon dioxide plus water, and then we are saying plus energy. It's always an exothermic reaction because energy is being released now. Now, what happens is C3H8 plus, you have to balance it. So you get 2 marks, 1 mark for the reactant, 1 mark for the product, but you have the third mark that you must get when you balance this reaction. And we have found it's much easier when you put the N in front of carbon dioxide, and they put the N plus 1 in front of water. It helps you to balance there. It becomes easier. Remember, C3, N is 3 because it's C3. So it means here you'll say 3CO2 plus N plus 1 is 4. So already you can see that we have 4H2O. Hence we have 3CO2 and 4H2O. Is the N and the N plus 1. And if you can check here, the carbons are 3, the carbons are 3. So carbons are balanced. If you look at your hydrogens, there are 8 here. 4 times 2 is 8, and you have 8 there. So just to put the N in front of carbon dioxide and the N plus 1 in front of water, already you were able to balance the carbon dioxide and the oxygen and the hydrogens. You are now left with oxygen. Hence we say hashtag sure, so that you know that I will balance the carbons by doing what? By putting N in front of the carbon dioxide. I will balance the hydrogens by putting N plus 1 in front of hydrogens. Now I'm only left with balancing of the oxygens now, because the carbons are balanced and the hydrogens are balanced. Let's check the oxygens. You have 3 oxygens, but times 2. So 3 plus 2 is 6. And then 6 plus 4 for oxygens is 10. So if you check, we have 10 there, and then we have O2 here. Already you have O2 there. Then you just divide this number of oxygen, you always divide it by 2. So if you have 10 this side, you say 10 divided by 2 is 5. And if you find 5 times 2 is 10. So the reaction is balanced, you are able to get 3 marks. Remember, the balancing is for the third mark. But the mark for you to write is the correct reactant and correct product, already you got 2 marks. The next mark is for balancing the reaction, which I just shown you now. I think that you will enjoy doing this. Even butane is the fuel in the big lighters. You know, the lighter, it uses butane. Remember, we said the importance of cracking. We said this chemical process that breaks down the large organic hydrocarbons into smaller, most useful molecules. You see the importance there. Bobutane, they will help you when you are having your big lighters there. You are able to use that. And you know how to balance direction. I just shown you. You will do the same. You will balance the carbons, you will balance the hydrogens, and then you will be able to balance that. Now, this is coming from our internal moderators report to say these acronyms are important, but you can't write them in the exams because we found learners when we find ways to make things easier for you. Now you want to write that in the exam as if that is the science. No, we're doing this for you to remember, not to forget. To say USA, we're saying when unsaturated becomes saturated, the reaction is called addition. When saturated becomes unsaturated, it is elimination. When saturated remains saturated, that is substitution. You have seen that with AHA, you are moving between from an alkane to a haloalkane, from a haloalkane to an alcohol. You have seen the two hydrolysis processes there. So I think you enjoy how to do this. And then we had that question. Now we are going to practice now the main thing, part of our lesson, because you see now intentionally we didn't put questions here so that you can now know that I must first analyze the information, because learners rush to answer questions. What are you responding to if you don't understand the problem? And so we're putting the problem before you there to say, look at this one. We have prop 1 in, and a science learner knows that prop 1 in is CH3H6. We have propane. Science learner will say, okay, carbon is 3, C3H8. So you can see the difference there. We have 6, we have 8. You can see that there are 2 hydrogens that have been added. So you will know that this is addition. What type of addition? The type of addition is hydrogenation, because you are adding hydrogen. What is the reaction condition? Platinum, palladium, or nickel. You see the importance of you now having to apply the knowledge that we're talking about. You're having a saturated there. You know, most alkanes, you know, we said AHA. They undergo either elimination or substitution. They undergo elimination or substitution. So you know, this is one of the AHA. It's alkanes. So it's either this reaction is elimination or substitution. And then you are able to check that. It's okay, we're having propane here. And then we're having Cl2. So you can see this is going to be substitution. Why? Because you are having a saturated forming another saturated. Remember we said triple S. Saturated is substitution. So you're having a saturated propane forming a unsaturated saturated haloalkane there. So that is a substitution reaction. What type of substitution? Halogenation. What is the reaction condition? Remember we said for this one, the very first one, alkanes to haloalkanes, we said we are going to use sunlight. You'll see in some books, they just show you sunlight as UV there. They are still referring to the same ultraviolet light, which is the light from the sun. So that is what we are doing. And then we are having another saturated forming another saturated. So you see now the triple S is helping in terms of this question, but there will be some questions when you cannot apply that. You got to just apply the signs. You know, the haloalkane that is formed there. You got to know that, okay, we have Cl2, we have propane. So you got to know that this is propane that we are having, and then this is propane that you are having, and then you are having Cl2. And I told you that the most stable product that will be formed is when your chlorine, your Cl, will replace this hydrogen in the where we have lesser number of hydrogen in this one. So the Cl will come to carbon number 2. So we are sure that for the major product it will be 2-chloro propane. That will be the haloalkane that will be formed there. But we know that the minor product is when the chloro is in carbon number 1. So it will be now 1-chloropropane as a minor product. Hence you see that now when it comes to this one, it's saying propan 1-ol. So you can see that it means now the chloro was in carbon number 1, which means we took the minor product. So you see the understanding of the minor and major product helps you when you start to analyze questions, because you know what is happening. So we took the 1-chloropropane and then we're able to replace the chloro in carbon number 1, which I can just show quickly. So you had a chloro in carbon number 1. Now we're replacing that chloro in carbon number 1, we're replacing it with the OH. It's still substitution because we're moving from saturated to another saturated. And the reaction is what? Is substitution. So you're able to see that, okay, we are now forming OH here. We're putting the OH there. Why did we do that? You can see that we want to form an ester. Remember we said for esterification, we use primary alcohols. Hence we are using primary alcohols. So you can see you're able to analyze the whole reaction and look at the reaction condition. Remember we said when you form an alcohol, the process is called hydrolysis. And we said there are two types of hydrolysis. You can use dilute sodium hydroxide and mild it, or you can use water and mild it. I hope you're enjoying the lesson, and then you will practice as many problems. Go to question papers, look for structures, you are able to see that. You can see there, we're having C2H4. It becomes C2H6. You can see that we have added the hydrogen there. You will call it hydrogenation. We said the reaction condition for hydrogenation is platinum, palladium, or nickel. So you are able to enjoy yourself there. And then you have ACl. You are adding ACl, which is hydrohalogenation. Remember, we said where we have alkene, all the reactions will be addition. So you know reaction 4 is addition because it's coming from an alkene. Reaction 2 is an addition because it's coming from an alkene. So you can be able to tell now that this is what? Hydrohalogenation. We're adding the hydro and the halogen. So you use hydrohalogenation. Reaction condition here, we said no water. No water must be present. So you are enjoying yourself, you are able to see all these reactions and you have no problem. Then you are able, they will tell you the product that is formed there. Obviously, it will be your chloroethane. Your chloroethane. You can see I'm not saying 1 or 2 chloroethane because we indicate the number if we want to show the position, if they are positional isomers. So because it's chloroethane, it doesn't matter where the chloro goes, it will still remain chloroethane. So you are able to see that, and then it can take place, further reactions can take place. Now let's look at practice number 3. Always you know that from an alkene, the reaction is addition. What are we adding here? You see that from prop 1 in to propane is hydrogenation, and the reaction condition platinum, palladium, or nickel. So I hope you see this and you say, yes, this is possible. We can do this. So every R that comes from an alkene, it must be addition because we can only add on the alkenes. The only reactions alkenes are undergoing in our syllabus is the addition reaction. So when you say an alkene, you know that it undergoes addition. So it must be addition, this reaction, which is hydrohalogenation. It must be addition here, which is hydration, because we're forming an alcohol now. And all the arrows that goes backward, you know, we're moving from saturated to unsaturated. So B must be elimination. What are we eliminating? Water. We're removing water, so you'll call it dehydration. And we said the catalyst there is sulfuric acid for both B and C, because when we see water, we know sulfuric acid will want to be around, with the exception of that water in the hydrolysis reaction, which we said the catalyst there, we just use mild heat and water. We don't use sulfuric acid for substitution reaction. So you are together with me there. Hydrohalogenation, this one, we said no water must be present. And then for D, when we are removing the hydro and the bromo, the hydrohalogenation, remember now you are going to use your concentrated sodium hydroxide. Remember we said this type of reaction will form an organic molecule plus salt, which is sodium bromide in this case, plus water. So you're able to see that reaction. And here you are having an alcohol which is saturated. You are having a haloalkane here. You are having a haloalkane that is formed from that one. So you can see reaction E is saturated, forming another saturated. So that is substitution. Reaction F is still saturated, forming another saturated. It is substitution. So you are able to analyze as many reactions as possible because you have done your basic correctly. So you can take as many question papers and continue to practice. Even here, you are having an alkene here, and then you are able to see that, okay, it becomes 2-bromobutane. It means we have added HBr there. Then we are getting 2-bromobutane. And then that one as well, in haloalkane can become an alcohol. Remember we talked about that. to say this is hydrolysis, where we'll use water and mild heat, or sodium hydroxide and mild heat. And alcohol as well can be able to form a haloalkane there, and we have indicated that you can use your HBr. We said we call it halogenation because it's Br. It's not all the HBr that is replacing the OH on the alcohol. It is the Br, hence we call it halogenation. So I hope you will continue to practice and enjoy this type of reactions. Now, in June 2021, we had this question that I felt very much important. It was having 8 marks to say ethane can be prepared from chloroethane by a 2-step process. You are supplied with the following chemicals. So you're given those chemicals. Select chemicals in the table above that can be used for this preparation. Remember, you are starting with ethane. You want to form chloroethane. Using condensed structural formula, write down a balance equation for each reaction. Indicate the reaction condition for each of the reaction. So you can be able to know that, okay, for this to be 8 marks, I must be using a 2-step process. So you can't say ethane and then you bring, for example, Cl2 and say I am going to form chloroethane, then we are done. That is not a 2-step process. So you know that an alkane can undergo elimination first, and then you can do elimination and add. So if you are having ethane, for example, you can be able now to have ethane, then it can undergo dehydrogenation, then it can become ethene, then you can bring HBr, and then we are saying no water, HCl. What are we forming? Chloroethane, and then HCl there, and then we're saying no water must be present. So it's very much important that you are able to do a two-step process, and with the proper planning you are able to do that, and then you are able to form the compound that you are supposed to form. So that, as I was saying, you will first get rid of the HCl there, which is the hydrohalogenation. You are using your concentrated sodium hydroxide, concentrated sodium hydroxide and heat, that is elimination. Then you are able to get your ethene there, your sodium chloride and water, and from there you add your H2, and then you are able to form your ethane. So you're forming ethane from chloroethane, but you must follow a 2-step process. So it's important that you can be given the synthesis type of reaction and you must be able to do them. So I just wanted to conclude by looking at last year's paper, November 2024, to say reaction 1 is a cracking reaction forming 2 compounds, W and T. So you can see we have W and T there. As the only product, define the term cracking. But they told you that it's a cracking reaction. So you know that we're having a large organic molecule, so we're going to break it down. Again, we're saying cracking is the chemical process where large hydrocarbons are broken into smaller, most useful molecules. So that is the 2 mark for defining cracking. Now, if you check, they are saying now, is the product in reaction to a primary, secondary, or tertiary alcohol, and then they are saying give a reason for your answer. So, but I want you to first analyze the diagram as we complete this question. To say you were given C4H8, which you know is an alkene, and I've told you that during cracking we form an alkane and an alkene, or an alkene and hydrogen. In this case, you are given another organic molecule, so it must be an alkane. But this alkane has how many carbon? This information is important because it's telling you that this alkane has 1, 2, 3, 4 carbons. So you know that I was having butane here, and butene will choose whether it's a put 1 in or put 2 in. We'll be told by the reactions as we go with them. But you can see that we had a butane and a butene, and then we'll check whether it's a primary or the double bond is in carbon number 1 or in carbon number 2 as we do the reactions. So you can see that we are having butane, and for us, if we are having alkanes, we know that alkanes are able to undergo a substitution type of reaction. So you can see there we have a Br there that is substituted. So you know reaction 2, it must be halogenation, where we had Br2. that will substitute the Br substituted the hydrogen from the alkane, and then we get a halo alkane. And then they're saying this halo alkane is going to undergo elimination reaction, meaning that we're going to remove the H, the Br and the H there. Then you can see that there we're going to have our product now, which will be our but1ene. Our but1ene that is formed there, then it further undergoes a further reaction, which is reaction 4, and then that product of reaction 4 will undergo reaction 5. And the first question was 4.2 to say, is the product of reaction 2, this one, is it a primary, secondary, or tertiary haloalkane? So you're able to know that this thing of primary, secondary, and tertiary is for haloalkanes and for alcohols. And we are saying, because this Br, the carbon, that is, it's good to draw a structural formula, because you will see clearly that you are having CH2Br like that, you are having the CH2 there, you are having the CH2, and then lastly you are having the CH3. So immediately when you have drawn the structure like that, you are able to see that, hey, now what am I dealing with here? You are able to see that, okay, this is a primary. Why is it primary? It's primary because the carbon that is bonded to the halogen is bonded to one other carbon. If it was bonded to two others, you will say secondary. If this carbon, the carbon bonded to the bromine, is bonded to 3 other carbons, you're going to say it's a tertiary haloalkane. But because the carbon that is bonded to the halogen is bonded to one other carbon, you're going to call it primary. That is your reason. The carbon bonded to the halogen or carbon bonded to the bromine is bonded to one other carbon. Hence, you are saying this is a primary haloalkane. Now, as we continue to complete our session, but reaction 1 is a cracking reaction forming 2 organic W and T as the only products that are formed. Write down the structural formula of compound W. Already you have seen that this was butene. We don't know but1 or but2ene. We'll see as we go on with the reaction, but you know it's butene with a double bond there, a butene, and then we're having butane here. So this is butane because we know it's an alkane and an alkene. So it was only when we substituted the Br, the hydrogen with the Br, that we got a haloalkane there. So you say that, okay, draw butane. They're saying draw structural formula of butane. Nicely, you are able to draw your 4 carbons and show all that as your hydrogens in your structure without any wasting of time, and then you are able to write CH3, CH2, CH2, CH3, and the cell structural formula, which means you must show all the bonds. Write down molecular formula of compound U. Remember, U now, you are having 4 and 4, so that must be octane. Remember, we do cracking of alkanes, so 4 plus 4 is 8. So you know that you can just add, because you know that C4H10 for butane. So what is C4 and C4H8 for butane? So you can see that it's a C4 plus C4 is C8. H10 plus H8 is H18. So you are able to see that this is a C8, H18, and that is compound molecular formula of compound U, and then you are able to do that. Now they're saying for reaction 2, write down the name of the formula of an inorganic reactant. Inorganic reactant, you know, we're talking about bromine there, because we're having an alkane, so we're bringing Br2 for substitution. And the reaction condition there, we said is sunlight, and then sometimes you like to write, or they asked as well, is the type of reaction substitution, addition, or elimination. You know this is an alkane that is undergoing halogenation, so you know that is substitution, because this is saturated forming another saturated, we call it substitution reaction. So you can see these are marks to collect. And then what is the reaction condition for that reaction? We said sunlight. So you're able to say sunlight and you get your answer. And then reaction 3. So we're moving with the reactions now. We're coming here. But what type of elimination? So they are saying already we know that this is an elimination reaction. We just want to know what type of elimination. So you know that you are having CH3, CH2. You are having another CH2 there. You are having a CH2 and a Br. So obviously we're going to remove the Br and one of the H is there. Then we'll have a double there. We'll have but1ene as our compound there, but1ene as the compound that is being formed. So what type of elimination? We're removing the H and the Br. dehydrohalogenation. Dehydrohalogenation. You know what we do? We said the reaction condition there, we can use concentrated sodium hydroxide. Remember, dehydrohalogenation is that one that we said it forms 3 products, which will be now an alkene, put 1 in. Our product is put 1 in, sodium bromide plus water. So you're able to write that, and I hope you are enjoying. You will practice and get as many question papers and continue to do this type of questions. Now they are saying compounds R and T are positional isomers. We've agreed. This one we said is put 1 in, so that one other one must be put 2 in. They are positional isomers. So that tells us that we are changing only the position of the double bond. But the inorganic reagents shown below are available for reaction 4 and reaction 5. Write down the balance equation for reaction 4 using structural formula and the correct inorganic reagent. So now you can see that we are having both 1 in, and then if we were to add Br2 here, we'll add the whole of it, which means we're going to get 1,2 dibromobutane, and then we don't do dehalogenation. So you know that this reagent is going to take you won't be able to remove to get the boot there again, put 1 in, put 2 in. So it's important that you can use Br2 there because we don't do dehalogenation. So if you form the product of put 1 in and Br2, they won't give you to get now T there. You won't be able to get T because we don't do dehalogenation. So we're disqualifying it like that. Now if we add HBr, for example, if we add HBr, if we are adding HBr, and then, or we can add HBr and then we can add as well H2. Then if we add H2, we are going to, if we add H2, we're going to get butane there, and then we're going to eliminate to get the but2 in, which will be the major product there. So now we have those options to say, okay, if we add Br2, we won't be able to go back there. If we add HBr, we're going to get a haloalkane, same as that one, which means we're going to get C, but the Br will be in carbon number 2. And then we're going to get H, because the H will go where there are many H's. So you will get 2 bromo, that one. And then when you're having 2 bromo butane, you can now be able to utilize concentrated sodium hydroxide. When you use concentrated sodium hydroxide, remember, you're going to eliminate the HBr, concentrated sodium hydroxide, you're going to eliminate that. So that is the reaction that you'll use. So reaction 4, you're going to use your HBr, then you will get your haloalkane, then your haloalkane will undergo elimination to get that one. Then you are able to get your put. We're going to remove that Br, and we're going to remove this H to get the major product. Remember the issue of the major product, we said we remove the hydrogen that will remove is from the poorer carbon. Remember that F's rule. We're going to apply it there. So you know that you're going to, for you to get but2 in, you're going to remove this bromine and that one. And what is the reaction? You are using concentrated sodium hydroxide. Then you will form your sodium ONOH, sodium bromide, and your water. Then you will be able to do that, and then that will be able to help you. So in terms of reaction 4, you are saying, okay, you're going to add your HBr there, and then when you add your HBr, this is the product that you are going to get. So you're just writing but 1 in, so the double bond is in carbon number 1, then you indicate all the hydrogens there, and then you add your HBr, and then you are saying, when you add the HBr, hydrogen will go where there are many hydrogens, hence you are having now H3 H's here. The bromine will go where there are lesser number of, sorry for that, there is no hydrogen there. The carbon must always have 4 bonds around it. So the bromine will go to carbon number 2, and then they are able to get it there. Then they got there, the bromine is in carbon number 2 there. Then you see now that is our major product, which is 2 bromo that. And then we're going to take sodium, concentrated sodium hydroxide, and then we're going to do now elimination of HBr, dehydrohalogenation, and form those products. Hence, we are saying write the balance equation for reaction 4, which is now this one plus HBr forming this one, which will now give you the 5 marks. This other reaction, you are taking this 2-bromo butane. What are you doing? You are using concentrated sodium hydroxide, and then you form sodium bromide and water, and then you are able to get the 3 marks. The IUPAC name of compound T, already we have named it as but2-in, because when you eliminate, we eliminate this bromo and this hydrogen. I hope you have enjoyed this lesson and you will practice as many question papers as possible. I like to end with these good words from Albert Einstein that say anyone who has never made a mistake has never tried anything new. Try as many questions as possible till we meet again. Thank you very much.